We're going to pick up where we left off. So you started filling in transformations on the back of the sheet, and we talked about translations, which was like shifting left, right, or up, down. We talked about reflections, which was like flipping. Vertically would be from up to down or down to up. Horizontally would be the stuff on the left would go to the right, and the stuff on the right would go to the left. Okay? And we talked about how some graphs, like the absolute value graph, we could see one kind of reflection, but you didn't necessarily see the other reflection in the way it was written because of the way the function behaves. Okay? So today we're going to talk about stretches and compressions. So based on what we wrote down yesterday, where do the horizontal changes seem to take place in the function? So if I have an absolute value function and I want to change something about it horizontally, would I expect numbers to show up inside the absolute value part of the function or outside of the absolute value part of the function? Inside. Okay, all the horizontal stuff seems to happen inside. If we want to shift it left and right, we add or subtract something inside. Okay? If we want to reflect it horizontally, we put the negative inside of whatever function it is that we're using. If we want to do something vertical to the function, the numbers tend to show up outside of the function. What I mean by outside of the function is they're still in the equation. They're just not in the part of the equation that does something special. Like they're not in the absolute value bars. They're not in the radical. They're not in the squaring or in the cubing. Okay? The numbers show up outside of that. So the same is going to hold true for stretches and compressions. Okay? For the vertical, or actually let's start with horizontal. For the horizontal stretches and compressions, okay, there's going to be something that shows up, and it's going to show up inside of the function. Okay? So when I denote it with my function notation, it's going to show up in here with x, not on the outside of the function. So if it's a square root, you're going to see this happen inside the square root. If it's absolute value, you would see this happen inside of the absolute value. Okay? So then the question, what is it? Well, when we add or subtract something, that doesn't stretch or compress our graph. It translates our graph, right? Left and right. If we multiply by a negative, that doesn't stretch or compress it. That just reflects it. Okay? So the operation we haven't used is we haven't multiplied by a number yet. So multiplying by a number on the inside is what's going to stretch or compress your graph. Okay? So when a number is multiplying x inside of the function is where you're going to see a stretch or a compression. Now the horizontal stuff tends to kind of remain a little bit not intuitive. Like you look at it, and when you guys saw x minus 3 in the absolute value bars, if you had to guess before you did anything what that would do, you would probably think left 3 because it said x minus 3. But what did it really do? Moved it to the right 3, right? So it's kind of the same with stretches and compressions. There's two categories. When the number you're multiplying by is less than 1. Now, I put absolute value bars around it because I don't care whether it's negative or positive, because the negative does a whole different thing. If we're multiplying by a negative, what kind of transformation does that do? We talked about it yesterday. It reflects, right? So the negative part is its own transformation. So when I'm talking about stretches and compressions, I'm just looking at the number part of A. So that's why mathematically I'm going to put the absolute value here to note it. So one kind of thing happens when A is less than 1, and a different kind of thing if A is greater than 1. Okay? Now, think horizontally. Okay? So horizontally, if you have your graph, stretching it horizontally goes this way, okay? Compressing it horizontally goes this way. So I have something that can kind of show you that. Take a minute to do that. We didn't really use the horizontal ones with absolute value because we just always factored it out to be a vertical change, and we'll see at the end of this discussion how vertical and horizontal stuff, they could be translated as both. Like you could say, oh, that's a vertical compression, but you might call it a horizontal stretch. We'll see. So here's an equation. Okay, it says y equals, there's an A outside the absolute value bars And then inside the absolute value bars, they have a b times an x minus h and then a plus k. So the h and the k shift stuff left and right. We would be talking right now about the b. The reason we would be talking about the b is because we're talking about a horizontal stretch or compression, and we said that's a number multiplying inside the function. So we want to see it multiplying the x inside the absolute value bars. So right now we're talking about b, not about a. Okay? A is going to do the vertical stuff because it's multiplying outside of the absolute value bars. So right now what I'm going to do on this graph is I'm just going to change the b value so you guys can see what happens. Okay? So right now it's set at 1 because it would be set at 1 in the parent function. So first I'm going to make it smaller than 1. What do you guys think is going to happen when I make it smaller than 1? Let's use language. Do you think it's going to be a horizontal stretch or a horizontal compression? Because we know it's in the horizontal world. Let's just take a vote. How many people think horizontal stretch? I'm going to make a less than 1. How many people think horizontal compression? Okay. All right, so then let's look at it, and then let's name it to see what we decide. So I'm making it less than 1. So it's going to go that way when I go less than 1. Would that be considered a horizontal? Because we're talking about horizontal right here, right? So to change the blue graph to what you see in orange, horizontally, would that be a stretch or a compression? A stretch. So when the number in there is smaller than 1, it actually causes a horizontal stretch. And this is why. When you think about the number that you used to plug in, so in the parent function, if you wanted to get a y value of 1, if you wanted the answer to turn out to be 1, what would you plug into the absolute value? 1. But then let's say I change the function so that there's a 1/2 multiplying the x inside of the absolute value. What would you have to plug in now to get 1? 2. So when I put a smaller number in here, what happens is you're not going to reach the height you reached before till you get a much bigger x to plug in with it to reach that height. So it's kind of weird that it works kind of like the opposite of what you would think. But with the horizontal stuff, when you plug in a smaller number than 1 here, it actually stretches it out because it takes you further away on the x-axis to reach the height you would originally reach before. Okay? So smaller numbers in there cause a horizontal stretch. Okay? All right, so let's go back and write that down on our paper so we don't forget. All right, so in our categories here, we have that horizontal is going to be seeing a number in here. I know I called it A and they called it B. It doesn't really matter what the number's called. It matters that you recognize that when it's multiplying x inside the function, it's going to be a horizontal stretch or compression. Then you're going to look at the value of the number. If the value of the number is less than 1, we just saw that actually causes a stretch. And if the value of the number is greater than 1, what do you think is going to happen? It's going to cause a compression for the same idea that when I put 1/2 here, it took you longer or further away on the x-axis to reach the height that you reached before. If I made this number something bigger than 1, like 2, what would you plug in for x so that the answer to this would turn out to be 1? 1/2. So now it's happening faster. It's reaching this height earlier than it did before. So all of a sudden you're going to see the height happen faster, the lines be steeper, or a horizontal compression. Okay. So when the number is greater than 1, horizontally we see a compression. Is this all right with everybody? Okay. So for an example of this, let's say we took a parent function, a quadratic. Let's say we took x squared. Okay. We'll give 2 different scenarios. One scenario, making this 2x squared. Notice that the 2 is inside what's being squared. That's how I know that this is a horizontal stretch or compression and not a vertical stretch or compression. Okay? Or I could multiply by something like 1/2 instead. Okay? So how would you say the graph has been transformed from the parent function? Remember that this is the parent function. If it becomes 2x all being squared, how would you list the transformation? What would you say has occurred? So make the decisions in your head. Horizontal or vertical? Based on where the numbers are here. Is the number inside the function, inside the important part that's happening, or outside of it? Inside of it. What kind of changes happen when you apply the numbers inside of the function? Horizontal changes. So this is definitely horizontal. Is it a stretch or a compression? So you know it's horizontal. Look at the number that you're using. Okay. Is it less than 1 or greater than 1? Greater than 1, which means it's a horizontal compression. Okay. So this is an example of a horizontal compression. And then we would often say by a factor of 2. Okay? Because there's different kinds of compressions. I could put a 3 there. It's still a horizontal compression, but now by a factor of 3, which is going to look a little different on the graph. Okay? All right. Somebody explain to me if we make this change here. If we go from our parent to this graph, f of x equals 1/2 x all being squared. How would you list the transformations that are occurring there? Anna?
Horizontal stretch by the factors of 1.
Good. Okay. So this is a horizontal stretch by a factor of, it's kind of hard to call it a stretch and then say it's a factor of 1/2. So sometimes because they say it's a stretch, you'll list it as the reciprocal. So you might say by a factor of 2 still. Okay? And here you might say 1/2. As a matter of fact, for us, let's do that because that's going to make your life easier when we graph it later. Okay? Because when we move around points, it will help you to think of each of these as the reciprocal. Okay? Is really what you're multiplying stuff by. Okay? Because when you horizontally compress it, they're getting kind of half as far as they used to be from the axis. And when you horizontally stretch it, they're really getting double as far as they used to be when we're using these numbers. If these were 3s, it would be triple and 1/3. Okay? Is this okay with everybody? Okay, so horizontal stretches and compressions. Right? What you guys saw when we did the absolute value investigation, we didn't leave the numbers inside of the absolute value. We always factored them out. So rather than viewing them as some sort of horizontal stretch or compression, once we factored them outside of the equation, we were making it a vertical stretch or compression. Okay? Because remember, the vertical stuff all happens outside. So for the vertical, this is still under stretches and compressions. Okay? For the vertical stretches and compressions, just like everything else that was vertical, this change is going to happen outside the body of the function. So in front of the squaring, or in front of the absolute value, or in front of the square root. So notation-wise, you would see the number still multiplying the function, but it's going to be on the outside of whatever the function is. Okay. And again, it's going to fall into 2 categories. Whether the number is less than 1, or whether the number is greater than 1. Okay? All right, so we saw this with our absolute value investigation. We called the A value specifically the number that was outside the absolute value. Okay? And what happened when that number outside the absolute value, now I'm not referring to negatives here, because if the negative is outside of it, it causes a vertical reflection. That's a different transformation. Here I'm just looking at the number part of A. Okay? If the number part of A is equal to 1, there has been no stretch or compression. It's saying it's going to stay the same width as the parent function was originally. If the number value of A is less than 1, what's going to happen? So what happened with our absolute value function when it changed to something like 1/3 and then times the absolute value? What happened just with how it looked? If it changed to 1/3 instead of 1. So you don't have to write this part down, but if instead of graphing this, you guys were graphing this, you already took a test and graphed stuff like this, how is this second graph going to look different from the parent function that would show up in the first graph? I don't need exact language right now, just how do they look different? Well, how does it affect the graph? Damien? Okay, good. It affects the slopes of the lines, right? Okay. Now, wider or narrower this second graph be? Wider. Okay, so let's say the first one looked like this, then the second one would be something wider than that, right? Is that okay with everybody? Okay. If this 1/3 number was written inside the absolute value, we would think about horizontal world, and we would call this a horizontal stretch because it looks as though it's been stretched horizontally to get wider. But because the 1/3 is written outside of the function, outside of the absolute value, this is no longer considered a horizontal transformation. It's considered a vertical transformation. What is happening to this graph vertically to turn it into this graph? Is it getting stretched out vertically to become this graph, or is it getting compressed vertically, which would make it turn into this wider graph? What do you guys think? If I took this graph right now, if I could take it off the paper and stretch it vertically, would it get narrower or wider? Narrower, right? But if I took it off and I could compress it together, the arms of the V's would be forced out to go wider if I squished it that way, right? So if it's getting wider vertically, what's happening is it's being compressed to be forced to get wider. Okay? So when this number out here is less than 1, when you guys saw that get wider, that was a vertical change, and that vertical change was compressing it to make it stretch out to the left and the right instead. Okay? So when the number out in front, okay, so vertical stretches and compressions, when you know it's vertical and it's less than 1, this is going to be a vertical compression. Whereas if that number had been equal to 3, you guys would have saw something narrower, okay? To get from this first one to this third one, if you could only grab the paper vertically, so on the top and the bottom, to transform this graph into this graph, would you stretch it out vertical or would you compress it vertically? Stretch it out so that it would become more narrow like that, right? So when the number's greater than 1 on the outside of the function, this is a vertical stretch. So it's a little bit of a bummer because the horizontal and the vertical ones operate differently. Basically, what helps me is I just remember that all the horizontal stuff is like wacky. It says x minus 3 inside the absolute values. It doesn't go 3 to the left. It goes 3 to the right. It says 1/3 in the absolute value. I'm not really timesing stuff by 1/3. I'm actually timesing it by 3. 3 is a big number. That's a horizontal stretch. Okay? So everything that's on the horizontal world is a little bit wacky. Okay, this is not mathematical, that part. I'm just telling you how I remember to do the transformations correctly. Once we've seen them, we could think it through, but do you want to have to think through this every single time? No, you don't want to have to plot points and experiment and figure out what's going on. What you want to do after you've seen it a couple times is say, okay, so the pattern is this. How am I going to remember this pattern? And then I'll use it when I come to doing the graphs. Okay? So again, I don't know if it's going to help you, but what helps me is everything, the horizontal changes are kind of opposite of what I think. It says plus 3, I'm going to go to the left 3. It says times 1/2, I'm actually thinking times 2, which makes me think stretch and not compression. Okay, so I'm thinking reciprocal of the multiplying stuff and opposite of the adding and subtracting stuff when it's on the inside. When it's on the outside, kind of like K, if it said plus 3 after the absolute value, you went up 3, it was very straightforward, right? Same exactly what you think with this. Okay? Small number outside the absolute value, smaller than 1, compression in the vertical world. Exactly how you think it would work. Okay? Large number outside the absolute value, stretch in the vertical world, just like you think it would work. So the vertical stuff is nice. What you see is what you get. The horizontal stuff is all kind of like It's just because of the way the graph works, right? We've seen that it works, but it's all kind of the opposite of what we might intuitively think just by looking at the number. Okay? All right, does this make sense to everybody? Okay, so just real quick, I'll do this a little bit differently. I'm going to write a parent function right here. Okay, so this is a cube root function. If this is my parent function, somebody give me an example of this function that would show a vertical compression, and then somebody else can give me an example of this function that would show a vertical stretch. So can anybody write this equation in a way, insert a number somewhere, okay, based on what we've said, that would cause this function to have a vertical compression? Tell you what, take 30 seconds with your group and come up with one that has a vertical compression and one that has a vertical stretch. Okay, now somebody give me an example of an equation for a cube root that would include a vertical compression. Yes, Elijah. Okay, good. But cube root x. So we're not changing the parent. Good. So all he had to do was multiply by a number, and the one thing was the number he multiplied by had to be less than 1. Okay? So that would definitely take whatever this graph looks like, which we will learn later, and it would vertically compress that graph by a factor of 1/2. Okay? So this would be vertical compression by a factor of 1/2. I don't really have to use the reciprocals of the factors here because of how we talked about how the horizontal stuff is like kind of doing the opposite of what we think, right? Here it's not. It's literally taking the distance you had before and it's like multiplying it by a 1/2. Okay? It's doing exactly what it says it looks like it's doing. Okay? All right, someone else. Give me an equation your group came up with for stretch. Sure. That's the cube root of x. So this would be a vertical stretch by a factor of 2. Is this all right for everybody? So the pro and the con. You got to totally understand what all these different numbers do in all the different types of equations. That's the con part. You kind of got to get all of that down, and it's a lot of information at once. Pro is, once you learn that information, we will use it the entire course. When we are at the end of our course graphing trig functions, we will still be using compressions, stretches, translations, and reflections. And if you get good at doing all of these things, every time we learn something new to graph, you're just going to have to learn the new original shape, and then you're going to go, oh, I already know how to do all the other stuff. I'm going to reflect it, shift it, stretch it, and you're going to be able to do all those things to any shape that I give you. Okay? So again, a lot of work initially, but really pays off for the rest of the course. The sooner you understand all of the transformations, the easier graphing every type of thing that we learn about is going to be for you. Okay? Any other questions about this? No? Okay, so Dylan brought up a good point. He said, let's say that I gave you guys this equation, and I asked you what the transformations were, because a horizontal stretch really is the same thing as a vertical compression, just depending on how you write it. So if I were to list the transformations of this equation, I would want to say the only change is the multiplying by 1/8. Multiplying by a number means stretch or compression. If it's inside the function, it means it's horizontal. So I would say this is a horizontal stretch or compression? Stretch, good job. By a factor of 8. Okay? That's how I would list it. And Dylan was saying, well, could you list it? Since you know the cube root of 8 is 1/2, okay, could you list it like this? If you show me that you rewrote it like this, then yes, you can list that as the transformations. If not, then no, because I want to see that you know exactly what each number is corresponding to. Okay? So I'm not giving you as much freedom there as you might like. If I give you a graph and I ask you to write the equation, you have a lot of freedom. Some people might choose to write it as a horizontal stretch. Some people might a vertical compression, all just how you looked at it and thought it was easiest to figure out. Okay? So are we good with the general idea behind all the transformations? Yeah? All right. Then we're going to do one of your doors. Okay? So turn over your organizer. So each of these doors is designed for us to put in each of the functions that we've learned. We've learned one function so far. Well, you guys should, you should know how to graph lines, so I kind of assumed that knowledge. But what is the function we have spent any amount of time in here graphing? Absolute value, okay? So one of our doors is going to be for the absolute value function. So on the front of the door, we're going to write the name of the function. We're going to write the parent function with its domain and range. Just a little sketch of the graph of the parent function. So on the door, I'm going to put absolute value. I'm going to make myself a little x and y axis. Again, it can be little. You're just sketching it. And I'm going to draw what the parent function of the absolute value graph looks like. Okay? So the parent function looks like a V. And I'm going to identify a few key points. So when we learn each new function, we're going to memorize what shape it looks like, and we're going to learn a couple of key points. But once we have those couple of key points, if anyone changes our function with numbers, we're just going to stretch or compress, reflect, shift, translate those points around the graph, and we're going to have the new graph very quickly. So a couple of things that I would point out is that the vertex is at 0, 0, and that we would have the point like 1, 1, and negative 1, 1. Things we should kind of automatically know about the parent function of the absolute value. Okay? And the equation for it would be f of x equals the absolute value of x. The last thing I want to write on the door, I know, sorry, is the domain and the range. Okay? So domain, x values. What are you allowed to plug in the function? In other words, you plug it in and it can actually be calculated and give you a result. Which x values are fine to plug in here and you can calculate a result? Are there any limitations? Usually it's nice to think about the limitations. Like when we thought about the square root, kind of identified like, oh, you can't do negatives. All right? So sometimes it's nice to think, is there anything you can't do? And then we'll write what we can do. Is there anything you cannot plug into here from the x-axis of the coordinate plane? No, there's no limitations. We can plug everything in. So we call that all real numbers, or we use the little symbol r. Okay? You're going to see another notation next year, interval notation. So I'm just going to kind of show that to you now. If it goes forever downward, we call that negative infinity. And if it goes forever upward, we call that infinity. And the way we write interval notation is we write from the smallest it can go to the biggest it can go. And then we write whether it's, you know when you graph inequalities, you have like open circles and closed circles, right? Whether you include the point or not. So for us, like a parenthesis is like an open circle and a bracket is like a closed circle. Like it reaches this point or like it goes here, but you don't actually do it. But infinity is like not really reachable as a number, right? My 5-year-old's always asking me like, Mom, how big is infinity? And I'm trying to explain to him like, it means just kind of, and then he's like, well, is 1 million bigger than infinity? Oh, okay. So he wants like a number for it. But infinity is not a number, so we have to use this. Okay? So this means the same thing as this. We'll get used to this. You don't have to be able to write this now, but include it so we get better at writing it later. Okay? All right, what about the range, the y values that we produce? Are there any limitations on the y values? Do you capture every y value? Only positives. Is 0 included? Yes. And do we actually reach 0? Yes. Like 0 would be like a closed point. Like we reach it. It's included. Okay. So we would say this with inequality. We would say that y has to be greater than or equal to 0. Okay. Now for this interval notation, what we want to say is 0 is the minimum, but we can go to infinity as the maximum. So we would list from 0 to infinity. 0 is an actual number that we reach, and we do actually reach that number, so it gets like a little bracket. And then infinity, because it's like an idea and not an exact number, can't technically reach it, so it gets kind of the open bracket. Okay? All right, then open the door. Okay? And behind the door, what we're going to do is we're going to do an example of graphing an absolute value function and listing out all the transformations with proper terminology. Okay? The graphing part's not going to be hard for you because you guys already know quick ways to graph absolute value. But the new part will be, can you state properly all the transformations that took place? Okay? So behind the door, okay, I know you have two sides to it. So on one side, we're going to graph the function, and on the other side, we're going to list all the transformations. Okay? So the equation and the graph on one side. So we're going to graph negative 1/2 times the absolute value of x plus 3 minus 1. Okay, so we kind of have our set way of graphing absolute value already, so we'll use that this time, and we'll get more into actually using the transformations to graph later. What do you guys know about the graph of this absolute value function? Amy? Sorry, sir. It's okay. It's okay. Okay, the vertex is negative 3, negative 1, and that's because we have had a horizontal translation of 3 units to the left and a vertical translation of 1 unit down. Okay, so negative 3, negative 1. So that point that used to be at 0, 0 for the vertex was translated here and here. Okay. All right, now what else do we know about our absolute value graph? Good, a slope of negative 1/2, which tells me it's facing down, and then the line should have a slope of 1/2 that way. So I'm going to go down 1 over 2, down 1 over 2. So this will be my graph. We didn't really use the transformation. We did, but we didn't. Definitely with the vertex, we used the translation idea. But there's going to be a more kind of set way that we can take a parent function and always use the translations to graph it, or transformations. But the absolute value is pretty simple compared to some of the other graphs, so we'll just use the way that we've always known how. Okay. All right, so next to this, on the other side that you left for your door, there on the back of the door or on the side inside, depending on how you did it, we're going to list the transformations. So we already said 2 of them. We said the translations, okay? We said that our graph was translated 3 units left and 1 unit down. What other transformations would be required to list here? CJ? Okay, but the way that the equation is written, unless you're going to rewrite that and somehow factor that 1/2 back in, the way that this is written is the 1/2 a vertical or horizontal change here? Is it inside the function or outside the function? Outside the function. What kind of stuff happens outside the function? The vertical stuff. So vertically, so unless you're going to factor this back in, which is going to affect this and this, okay, I would list this as a vertical transformation. And what is it? A vertical what? Compression. Do you guys agree with him? Yeah, because vertical is kind of like what you see is what you get. So there's a vertical compression. By a factor of 1/2. All right, is there anything we haven't listed? Yeah. Good. It was reflected because we multiplied by a negative. Is this a vertical reflection or a horizontal reflection? So it's outside of the function, right? It's outside of the absolute value, so it's a vertical reflection. So there was also a vertical reflection. Yes. No, because times 1/2 will compress it. The horizontal stuff works the other way because of the way that like how we saw on the graph, what you have to plug in to do that. Okay, so each time we learn a new function, we're not going to take any more notes on the back of this. You have all the transformation information. But each time we learn a new type of parent function, we're going to graph that parent function on the door, talk about its domain and range, do an example of it with the transformations. One last question on this graph right here. The domain and range may now be different than the previous graph. What is the domain of this function? Here's how my friend likes to say it if you're struggling. What does she use? She literally has a Jay-Z finger puppet, okay? And she uses like Jay-Z and Batman. And so Jay-Z is like the domain because he has to move like across the stage while he performs. So you think if Jay-Z is like walking on this thing and this is his stage, is there any place he's going to hit a hole or it's going to end? No. So left and right, you're good. You can go anywhere you want. So all real numbers. I know. It's kind of weird. But she rocks her finger puppet. Okay. So then she uses Batman for the range because he climbs up and down buildings. Okay. So if Batman's on here and he's walking all around on it or climbing it or whatever you want to think, but now you're thinking vertically, okay, up and down, okay. As he's going down, is there any place he's going to hit? No. As he's going up, is there any limitations? Yeah, the building ends right here, right? Okay. At -1, so that's where our vertex was. So in this case, y is, there was no problem going down, but you hit a maximum, so y has to be less than or equal to -1. Or in other words, it goes from -infinity to -1, which is the maximum. Okay? All right, so tonight's homework is all based on just kind of general transformation stuff, kind of written in the notation that we wrote on the back of your handout. So I'm going to project what the homework is. It's going to be number 3 on your assignment sheet because you've done 2 already. Okay? You did the 3 equations, 3 unknown thing, and then you did the linear programming handout. Those were 1 and 2.